Okay, thank you so much, Daniela. We're going to move to the next presenter. And if we can have our next presenter, and this will be a recorded session. As a reminder, we are recording this symposium sessions speaker series. We are, as a reminder, after this, going to be breaking. So please welcome to the stage Kyle Rex from Organization 8421.
Howdy, my name is Kyle Rex, and my project is working on developing a method to obtain a Bodie plot of a live switch mode power converter and comparing the results with simulations. So a little bit about me: I'm a mechatronics engineer at Texas A&M University, and I'm a summer 2024 virtual intern working at Texas A&M. So the objective of my research is to create a tool chain to model a switch mode power converter and feedback controller and to validate the closed loop controller performance with hardware measurements. So the overall background and supporting mission of this is to broaden the understanding of switch mode power converters to ultimately help in the implementation and development of radiation hardened technology to use in systems to respond to nuclear disasters or space applications. So, kind of the overview of my project, my focus is on a buck converter and type 3 compensator and using transfer functions of those to create Bodie plots using MATLAB. So, as you can see here, a buck converter is made up of a voltage source, an inductor, a capacitor, and some sort of load. And you can see the difference between the accounting for parasitic resistance, which can be shown in the Bodie plot you see in the middle there. The red is with the parasitic resistance. As you can see, it has quite the effect on the phase plot, bringing it back to that negative 90. And then using MATLAB, that was created, and using those transfer functions, we were able to model that. So then with the type 3 compensator, the type 3 compensator is going to be used to stabilize the buck converter. And as you can see here with the Bodie plot, it has that 130-degree phase boost in the phase plot. And the type 3 compensator feedback controller itself is made up of an op amp, two compensators, and a voltage divider, and a reference voltage. And as you can see there's the transfer function, and yes. Okay. And then really, like I said, the type 3 compensator feedback controller is used to stabilize the entire system. So as you can see on some of these plots below, you can see the buck converter, and then you can also see the type 3 compensator, and then you can see the resulting plot of the closed loop response for the system. And that was kind of the main goal, was simulating the closed loop response for that system. So then the next part of my project is, as well as using the transfer functions to create those Bodie plots, is comparing those to actual Simulink simulations and comparing them. So as you can see here, I created a buck converter in Simulink, and I also created a type 3 compensator in Simulink. And at first it was just about creating them. And then once I created working ones, it was about configuring the values to show to replicate what we were trying to use. And once the values worked and once the simulations worked, the next step was developing a code sequence to get the transfer function from these models. And that's what you can see here, creating the MATLAB coding sequence to get that transfer function that I was showing you in those earlier slides. And then as you can see here, the Bodie plots, these are the resulting Bodie plots of those transfer functions we got from the models. And as you can see, they are similar, but there is a little difference. And I'll talk about that later on. But then, yeah, the last step, the main focus of my project was creating Bodie plots from hardware. So creating a hardware tool set and test procedure was my main focus. And so part of that was picking a circuit that I could test. And the circuit that I ended up choosing was this circuit right here that had clear open points that I could inject the signal across a terminating resistor and measure the input and output response to get the frequency response of the buck converter and the compensator. So as you can see, there's the ideal Bodhi plot in the top right, and that was another goal. We needed to see what the ideal Bodhi plot would look like, so we had a reference for creating this tool set and creating this procedure that ultimately the goal was to get that Bodhi plot on this physical converter. So, like I said, developing the hardware tool set involved quite a few different things. One of the implement things that part of this is the injection transformer, which injects a sine waveform across that terminating resistor that I was showing here before between those two input and output Bodhi points. And that was the big breakthrough with finding that injection transformer, as well as getting the licensing products for the oscilloscope itself to do the frequency analysis plot. And then after the tool set was created, the next part was actually setting up the test and creating the procedure and ultimately executing. And as you can see here, like I said, the whole focus was across that terminating resistor and injecting the waveform and then measuring the input and output response to create that frequency response waveform. So ultimately, you can see here, using the oscilloscope, I was able to create a working test procedure and tool set that would create the same Bodhi plot you can see up in the top right there, on the physical scale. So this allowed us to then use this method to also test other power converters that we're developing to ensure that the frequency response is what we want it to be. And then, yeah, in conclusion, the regrets, like I said before, we there was a little difference in between creating the models and the real life result, and that was something that we've dived into more recently. And then next steps, what I've been doing recently is actually, really getting into the integral parts of it and developing a physical test circuit of all those components I showed you earlier, and really taking that smaller TI converter right there and really making it much larger and developing the physical aspect of that. And yeah, that is it. Thank you. Any questions?
Thank you, Kyle. If there are any questions, please raise your hand in the auditorium and we'll come around with the mic. And if there's any questions in the chat, please put them in the chat.
Yeah, thank you for your presentation. My question is, how closely did the live measurements align with the MATLAB simulations?
Sure. So when it came to ultimately, that is something that we've been working on more recently. At the time of creating this presentation, I had just basically finished creating that test procedure and test structure for actually getting the Bodhi plot itself. So recently, I've been really trying to look more into using LT Spice specifically to try to simulate some of these, because there's some limitations for the current software we're using to simulate some of the things that you see in that TI module. So I wasn't able to actually create that Texas Instruments model exactly as it is shown in the previous slides. But ultimately, that is the goal, and that's why I said that what I'm focusing on now is developing a physical converter that I can accurately model in a software, and so we can really dive deep into seeing the exact same results.
Thank you.
Maybe I missed it, but from what I gathered the MATLAB and Simulink the Bodhi plots were different, correct? So why do you think that's like the reason they're kind of on the same platform?
Yeah. So even with so like I said, like I was talking about here, deriving that transfer function. Originally looking at some of these transfer functions, they don't account for everything that goes into a live circuit, and that's the problem. These are just so simplified transfer functions that it really takes super simplified, and it kind of misses out on some of the real life circuit applications. And that's why you can see the difference in the Bodhi plot from the MATLAB itself and the simulation as well. With when it comes to the coding sequence itself, getting that transfer function was a real challenge, and it was kind of hard to accurately model that. So it's still a work in progress.
Okay, thank you so much, Kyle, for presenting today. Let's